This video is about regression. We're going to talk about linear regression, polynomial regression, exponential regression. It's also about the coefficient of determination, r squared, and how to use it to choose between different possibilities of regression that you can use for the same data set. But mostly it's about reflecting upon your results and how simply going through the processes correctly and looking at a number that a calculator might have given you as an answer, even though it's correct, might not be enough to do the best things that you can do with your data. So linear regression is present in all 4 of the IB courses, but the other types of regression that we're going to talk about are not. They're only in the AI HL course. Personally, I don't think there's much of a reason for that, because both conceptually and mechanically on how to do them in the calculator, they are very, very similar to each other. So I believe that this is a topic that students of all 4 courses should know about, because it can be very useful for a lot of things that you might want to do in an IA. So let's go ahead and explore all these things through an example with 10 data points that I'm going to be doing different regressions on. Set of points I just created because I wanted something that didn't look linear. And I'm going to be using this spreadsheet version of GeoGebra to do the regressions. It's not even the only way that GeoGebra knows how to do regression, and it's obviously not the only tool for regression that you can do. In the TI-84, the things are right next to each other and they work exactly the same. In that menu, when you have the linreg, the linear regression, like right next to it, you have quadratic regression, cubic regression, exponential regression. But what I want to point out in the video is the following. When you do the linear regression, and let's do it for these points, of course, it's not a very good line because the data doesn't look linear, but whatever technology you're using is just going to do the best line that it possibly can. So I'm circling down in yellow down here in the bottom of the screen the fact that I chose linear regression, the line of best fit that he gave me, and up here I also circled in yellow something that is called r squared, and it's 0.7205 according to him. R squared is something that the calculator, the TI-84, is also giving you. A lot of students ask me this. Why does he give me both r squared and r if r squared is just r squared, right? You could just square it. But they are two different things, okay? So the r is the Pearson's correlation coefficient, which is something that we use in linear regression to determine how strong of a correlation that is. And in the case of linear regression, the r squared really is just r squared. But the thing that is interesting about it is that only linear regression has Pearson's correlation coefficient, only linear. But r squared is something that we can generalize to other types of regression. That's called the coefficient of determination. Don't talk about Pearson's correlation coefficient if you're doing a regression that is not linear. Only if you're doing linear regression you can talk about Pearson's correlation coefficient. But for any type of regression that you're doing, it's okay to talk about the coefficient of determination, which is this r squared. And as we can see, 0.72 is the square of some number. I'm going to let you calculate that. It's not exactly a very strong correlation, right? Which makes sense because our data didn't look linear in the first place. And a very common idea is that you can choose different types of regression for the same set of points and then compare the coefficient of determination for those various regressions, and whichever one has the biggest coefficient of determination will be considered a better fit for the data. I think that makes sense, right? Because the coefficient of determination 1 would be perfect fit, and then the closer it is to 1, the better the fit. Yeah, makes sense. So you're looking for a big coefficient of determination. You're going to try a bunch of different types of functions for the regression using technology. You're going to compare them and choose the best one. That is the basic idea. but there's going to be something else. So let's start doing this for this set of points. Okay, notice here in the bottom that I chose polynomial of degree 2. So it's fitting a parabola, giving me the equation of the parabola. You can look at the picture. Maybe it looks slightly better than it did before. Maybe it doesn't. I mean, to an extent, this is subjective, right? Do you think it looks better? And then you look at the coefficient of determination, and it has become a lot bigger. It's 0.8994. So if you're just going by the numbers, not asking yourself any subjective question at all, this one is a better fit, a polynomial of degree 2. But of course, we're going to go ahead and try degree 3 next. In the very bottom left of the screen here, please ignore the fact that GeoGebra refuses to show the number 3 there. So it's going to look like polynomial of degree 2 in all of the following images, but just focus on the function, not on the number in the corner, and everything will be fine. The coefficient of determination is even bigger for this one, is 0.92. And subjectively speaking, I think that I would probably go with this one for this data. I would definitely not go with the line, because even with no regression on top of it, these points don't look like a line at all, right? They start looking really horizontal, and then they start going up. So it could be 2 lines, but not 1 line. And the parabola, I wasn't really a big fan of the parabola, because the parabola goes down and then up, right? It was a parabola with positive concavity. But this doesn't go down and then up. It just goes up. So I didn't personally like the parabola for this data set for that reason. But the cubic is looking okay. Let's go see the next one. And remember, the coefficient of determination was 0.9209. This one is bigger. I forgot to circle the numbers on the screen, but you know where to look for it, right? This is degree 4. It's looking better. Oh, okay, so maybe I would choose this one instead of the cubic, right? If I'm trying different things. It didn't get that much better in terms of the coefficient of determination, but then again, visually, it also doesn't look that much different. So I guess I could choose either one. Depending on what I'm going to want to do with it later, you also, maybe you want a simpler function. If you're going to have to do calculations with it later, you might want to simplify. If they both look equally good, and they both have a good coefficient of determination, maybe choose for the simpler one for ease of calculations later on. And in this case, that would be the cubic, not the quartic. But let's keep going. Let's see the next one, degree 5. And this is when things start to look weird. Because again, we see a slight increase in the coefficient of determination, but then again, it's already quite big, right? So it can't really get a lot bigger because it's already almost 1. But it did get a little bit bigger. However, visually, when you look at it, the part that I circled in yellow here, that has a local maximum and a local minimum. That doesn't look like it should be a feature of the data points. They don't look like they're doing that. They look like they're going in a straight line. So it's kind of weird to choose a regression function that does other things on top of the things that the points are doing, right? So you're getting a better coefficient of determination, but the point that I'm trying to get across to you is that getting a good coefficient of determination is not the only thing that you want. So don't just go blindly by the numbers. Also check to see how your functions look. Do they seem to make sense with the data? And I think for this data set, degree 5 is already going too far. But for the purposes of this video, I am going to keep going. That's degree 6, and it's extremely strange. Okay, so it still has around the first points, the same thing with the local maximum and local minimum, but it's looking even stranger than the previous one, right? After the local maximum and the local minimum, it keeps increasing for a long time, but it has like these subtle changes in concavity. I have no reason to think that the original data set had that feature. So this is not good as a regression, even though the coefficient of determination has still increased some more. And the thing that I circled in yellow here is, listen, even though we tell you that interpolation is good and extrapolation is bad, and you are still supposed to answer that in exam questions, remember, interpolation is good and extrapolation is bad. However, in practice, sometimes you are trying to do extrapolation, especially if your horizontal axis is time. Being able to sort of predict the future, even though you're not going to be accurate, is still something that you might want to do. So these points have been following this trend so far, and I do want to extrapolate to see where they're going, but look at the points. Do they look like they're going to take a sharp turn and just go down after that? No, that's not what the trend of the points is telling me, but that is what this degree 6 polynomial is telling me, even though it has a really high coefficient of determination. This is a really bad regression function for this data set. Let's go even farther. Whoa! So I think I skipped 7 and 8 because they weren't introducing any more strangeness, but this is degree 9. This is, wow, the coefficient of determination is 1. That is a perfect fit. However, that's not what you want, right? What's happening here is simply that my data set had 10 points. And this is a general fact. You know how if you have 2 points, you can always pass a line through them. You can find the equation of the line that goes through 2 points, right? This is a basic exercise. So 2 points, line has degree 1. Did you also know that if you have 3 points, you can fit a parabola through them? You can always do that. So 3 points, equation of degree 2. That is a general fact. If you have n points, you can always perfectly fit a polynomial of degree n minus 1 that's going to go exactly through those points. That is an exercise in solving a system of linear equations. If you plug in your points to the general expression of a polynomial, like say it's degree 6. So ax to the power 6 plus bx to the power 5, and so on and so on. And you had 7 points, then you will have 7 equations in the 7 variables a, b, c, d, e, f, g. It can always be done as an exercise in solving a system of linear equations. It can be annoying, but you can also use matrices to do that, so whatever. That's not regression though, not really, because those points, they go through the polynomial perfectly. And the thing that regression is good at is when the data set is not perfect. They follow something of a trend, but they're not fitting perfectly. So what I was trying to illustrate here is that in the extreme, if you're going after that coefficient of determination equals to 1, you will find it, because it will just be a matter of solving a system of linear equations in the end. But it's not going to be useful for any context that you're using this. If something has to be the moral of the story for this video, it's this. Yes, compare a bunch of different regressions. Yes, look at their coefficient of determination, but bigger is not always better. You also have to look at the picture and subjectively decide which one is better. Of course, polynomials are not the only functions that exist. In fact, when I look at just the points, I kind of see something exponential, right? Something that starts very horizontal and then takes a kind of a sharp turn, starts going up. This purple line here was drawn by hand, which is why it doesn't look very good. That's what I see when I look at the data. I see the purple thing that I drew by hand here, but now I want to try to get the technology to do this for me. But when I gave this Same software, and I told him I want exponential regression. Look at the bottom left corner here. So that is an exponential, but the red line that he drew doesn't look good at all. I want my purple line. I don't want this red one. And even the coefficient of determination is kind of bad, is 0.78. That's not what I wanted it to do. But the thing is that the kind of exponential that he is looking for doesn't have this vertical translation that I want. He wants an exponential that is just constant times e to the power of constant x. And that is equivalent to, if you didn't require the base to be e, it could be like constant times another constant to the power of x, because the rules of log will make it so that this is equivalent to that. But you see in the vertical axis here that my original points are oscillating between 4 and 5. So that's kind of where I wanted the asymptote to be. I didn't want an asymptote at 0 like this function that he is giving me has. I started trying to do this by hand, but that was before I learned the proper way to do this in GeoGebra, and I'm going to show you in a minute. But the purple line is the one that he had given me, and the gray one is me trying with the sliders to get to something that has that plus D in the yellow circle that I put there, because I want that vertical translation. I was trying to do that by hand by moving the sliders, but it's very difficult because I had like 4 constants, A, B, C, and D, and they all interfere with each other. You can try to do that just to practice like graphical transformations of functions and see if what you're expecting to happen when you move one of the sliders is actually what's happening on the screen. But I really don't recommend this as a method for regression. This was kind of the best thing that I managed to do with the sliders. It's not very bad, but I have no way of guaranteeing that this is the best in any sense, because it was just trial and error by hand. So this is what you're going to do. You're going to have all of the points typed in there. You see they're labeled A through J. And then you use this function that you see on the bottom left corner of the screen here. It's called fit. And then you put the list of points, just all the letters there, comma, and then you type the expression that you want, the kind of expression that you want, with any constants that you want him to find. So I had A, C, D, and K. I had 4 constants because those are all of the translations and stretches, right? I have a vertical and a horizontal translation, a vertical and a horizontal stretch, and he came up with this function. It's 0.16 e to the power of 0.44x minus 0.74 plus 4.15. Look how well it fits the data. This is the one that we had been looking for all along. And the other interesting thing that I wanted to mention is that even though perfectly fitting a polynomial through a set of points, like a parabola through 3 points, is not regression, if you happen to run into a question like that in an exam, and it is an exam that allows a calculator, you can still use the regression tools in the calculator to solve that kind of problem. In this example, 3 points fit a parabola, it would be a quadratic regression. So the only thing that you're going to do is to pretend that you're doing quadratic regression, but your data set is only 3 points. The answer is going to go perfectly through the points, and there you go. That's going to be the answer to the question. Of course, this will only work if the exam is allowing a calculator, but still, it's a nice little thing to know, I think. And in the next video that I'm going to post, I'm going to be exploring these regression topics in the context of an IA. It's going to be my second example of an IA that I'm writing myself.